Today we're going to talk about lesson 3 on the ideal gas law. Some of you may be wondering what is meant by the term ideal and how it is different than something that is not ideal. So if you look behind me, it says that the ideal gas law states that the pressure, volume, and temperature of a sample of gas are directly proportional to the number of moles of that gas. You heard right, moles are back. Just finishing them with stoichiometry, and now we're bringing them back to introduce them into our new unit on gases. Now, the ideal gas law makes use of two assumptions. Number one, that molecules and atoms have no attraction for one another. Technically, that's not 100% true. And we'll find out how our calculation is changed as a result. The second assumption that we're going to work with is that molecules have a volume that is negligible compared to the volume of the container that they're in. Now, depending on the concentration, the number of molecules that are in the container, this may or may not be a valid assumption. But we're going to work under that premise to ease our calculations. If we look, our equation for the ideal gas law is simply pressure times volume is equal to the number of moles times a constant, which we're going to call the universal gas constant, R, times a temperature. It's important to note that unlike when we were completing problems for Boyle's, Charles, and Gay-Lussac's, now we are going to have to use a specific unit for pressure and a specific unit for volume. So if we are presented with units other than ATM for pressure and liters for volume, we will have to convert into those two units in order to solve our problem. Just like we have seen earlier, temperature is always going to be measured in Kelvin. The universal gas constant, R, is exactly that, a constant, meaning anytime that we need to use R in an equation, we get to use this number, 0.0821. This is the unit for it. It's a complex unit, and it incorporates both liters and atmospheres, moles, and Kelvin. This begs the question, what if we didn't have an ideal gas? What if we were doing really precise calculations and we were concerned with real gases, what we actually see in reality? So this equation is similar to what we had on the previous page with our PV equals nRT. However, a corrective factor is placed into both the pressure and the volume part to account for not only the attractive forces between molecules, which is why we must add a little bit to our pressure values, but also subtract out the volume of the molecules themselves. Now, we are not going to perform calculations where we have to use this kind of expanded formula for PV equals nRT. Notice that there are two constants, A and B, that we would have to make use of for each gaseous molecule that exists. We're not going to do that. For our purposes, PV equals nRT provides us with a numerical answer that is close enough to reality that we can go with. Let's take a look at our first example. As we've done in the past, I'd like to begin by identifying what the variables are on the left-hand side. So since we are learning about ideal gas law, we are going to be concerned with pressure, volume, the number of moles, and the temperature. R, remember, is a constant. It's always known. It's not going to be given to you in a problem, but it's always going to be there. So we can fill that in automatically as 0.0821 liter times ATM over moles times Kelvin. Now, let's read through the problem to get our other variables. A 2,500 milliliter cylinder. Remember, when we're talking about gases, the volume of the container is our volume. So we're going to start off with our volume of 2,500.0 milliliters. Contains hydrogen gas at a pressure of 2,280 mmHg. and a temperature of 25.10 degrees Celsius. In this case, the question is asking us to identify the number of molecules in the container. Now, you might recall from our map earlier on in the school year that before we can get to molecules, we have to get to moles first. So moles is our unknown in this problem. Okay, let's take a look at the equation for the ideal gas law and solve for our unknown variable, moles. So we have PV equals nRT, but we're solving for N, the number of moles. So we're going to wind up with an equation that is N equals PV divided by RT. Now, before we can substitute into that equation, we have to go back and do a unit check. Do all of our units match the units that we need in order to use the ideal gas law equation? The short answer to that is no. We have to convert our pressure, volume, and temperature before we can use it in our equation. So first, looking at our pressure, we're provided a pressure in the units of millimeters of mercury, but yet we need to be in units of ATM in order to put it into our equation. So we have to convert from mmHg to ATM by dividing by 760. You're going to be provided a list of these constants that would be necessary in order to do these conversions. So over here, we're going to divide by 760 mmHg for every 1.00 ATM. This gives us a new pressure of 2280 divided by 760 or 3 ATM. Maintaining significant figures, we're going to write 3.00 ATM. Our volume must also be converted from milliliters to liters. This is done by dividing by 1,000. In order to maintain the same number of significant figures, I'll have 2.5000 liters. Finally, our temperature has to be converted just like we were doing earlier from Celsius into Kelvin. So our 25.10 will be added to 273.15 for a total of 298.25. Remember, whenever you are converting from Celsius to Kelvin, you're going to add 273.15. Okay, we now have all of our units in the correct form that will allow us to use it in our ideal gas law equation. So now let's take a look at our equation. We have P times V. So our pressure, 3.00 ATM, times our volume, 2.5000 liters, divided by our value for R, 0.0821 liter ATM over mole Kelvin, times our temperature, 298.25 Kelvin. Remember, when you are dividing, if you have two numbers on the bottom, you have to divide by both of them. You can do this either by enclosing them in parentheses, or if you're using a traditional calculator like I am here, hitting divided by before you enter each number. So on the top of my equation, I'm going to have 3 times 2.5. Then I'm going to hit divided by, and I'm going to type in my value for the R, the universal gas constant. And now, because the temperature is also on the bottom, I'm going to hit divided by a second time, 298.25 for a total of 0.306. So in this case, our number of moles of hydrogen turns out to be 0.306. Now, we didn't actually answer the question just yet. In order to get into molecules of H2, we have to multiply by, and this goes back to October, we have to multiply by Avogadro's number. That is our bridge from number of moles to the number of molecules. Okay, so now it's time to type this into our calculator. I've opened up my graphing calculator so I can use the exponent function, which my other calculator did not have. So in this case, I have 0.306 times 6.02 exponent, which is second, and then comma, that'll bring up the e, times 10 to the 23rd. So my final answer ends up being 1.84 times 10 to the 23rd. Okay, so there are a few ideal gas law problems that I would like you to try out. They're very much like this ideal gas law problem. Now, before I let you go, there are two other problems that I would like to show you. So the first looks at our conditions at STP. Now, you may remember from a previous video what is meant by the term STP. It is a shorthand way of telling you what the temperature and pressure of a system are. STP, as a reminder, stands for standard temperature and pressure. Now, standard temperature and pressure means something. There is a specific temperature known as 0 degrees Celsius or 273.15 Kelvin that we use to talk about standard temperature, and our standard pressure is going to be 1.00 atm. So when you are told that a system is at STP, that's a shortcut for temperature equals 273.15 Kelvin and pressure equals 1.00 atm. So when you read this in a problem, you'll automatically know the temperature and pressure that you need to use for your calculation. Let's take a look at the rest of the problem. In this problem, it tells us that we have 1 mole, exactly 1 mole of hydrogen gas. So our value for N is going to be 1 mole. And we now know our temperature and pressure terms. So 273.15 Kelvin, 1.00 atm. Remember, R is a constant, meaning it is always going to be the same number. It's always known, even if it's not explicitly stated in the problem. So we can go ahead and fill in R as 0.0821 liter atm over mole Kelvin. In this case, we're going to use PV equals nRT to solve for volume. Let's do a quick check of our units to make sure that we have what we need moving forward. Our pressure is listed in ATM. We're looking for a volume that will have answers of liters when we find it. We have number of moles in moles, and we have our temperature in Kelvin. So we're ready to proceed with our problem. Looking at volume. Volume equals our number of moles, that's 1 mole, times our unit for R, 0.0821 liter atm over mole Kelvin, times our value for temperature, 273.15 Kelvin. All of that divided by our pressure, 1.00 atm. When we solve for volume, we will end up getting an answer of 22.4 liters. Go ahead, type it in and try it yourself. Now, it turns out that the way I knew the answer was 22.4 liters has more to do with the fact that at STP, 1 mole of any gas in existence will occupy a volume of 22.4 liters. It's known as molar volume for gases, but I wanted to show you where it came from before we used it in a problem. Let's take a look at example 3. Now, in this case, we also find ourselves at STP, standard temperature and pressure. So a temperature of 273.15 Kelvin and a pressure of 1.00 atm. The problem tells us that we have 1,500 milliliters of our substance. So our volume is going to be 1,500 milliliters, but yet I know that I have to convert that into liters before I can use it in my problem. So dividing by 1,000, 1,500 milliliters will become 1.5 liters. And of course, we always know our value for R. So in this problem, we're going to solve for the moles of ammonia and eventually convert that into mass. Now, you can actually save yourself some time using the conversion that we learned in our previous example. If and only if we are at STP, we can use a shortcut. 1.5 liters of ammonia, but again, this would work for any gas, has a volume of 22.4 liters for every 1.00 moles. The answer that we obtained from problem number 2 is something, again, that is universal. Anytime we are at STP, we can use this conversion factor to go directly from volume of a substance into moles of a substance. So in this case, we'll have 1.5 divided by 22.4 to wind up with a number of moles equal to 0.0, we'll go with 3 significant figures, 0.670 moles. Again, this conversion going directly from liters into moles only works at STP. Some students try to use it in different temperature and pressure situations. Your answer is going to end up being incorrect if you do that. So it's a great tool, it's a great shortcut, but its use is very limited because you can only use it under STP conditions. Okay, let's finish up this problem by converting from moles into grams. So I would take my 0.0670 moles, multiply it by 17.04 grams, which is the molar mass of ammonia that you would find on the periodic table. You get an answer of 1.14 grams of NH3. Notice in this case, my unit of moles and moles drops out. Let's take a look at one of the homework problems. So looking at our assignment for tonight, I'm asking you to only do the even numbered problem. But let's take a look at problem number 1 together. It says, if I have 4.00 moles of a gas at a pressure of 5.60 atm and a volume of 12.00 liters, what would my temperature be? So we're going to start off using the full equation, PV equals nRT. But again, we don't want to solve for pressure or volume in this case. We're trying to solve for temperature. So temperature is my unknown. And remember that we always know the constant 0.0821 liter times atm divided by moles times Kelvin. Now, knowing this, we can solve for our temperature. So in our case, temperature is going to be equal to PV over R times N. Now, substituting into our formula, our temperature is going to equal our pressure of 5.60 atm times our volume of 12.00 liters divided by the number of moles, which in this problem is 4.00, times our value for R, which is 0.0821, or you could simply type in R. Solving for temperature. I'm going to bring up my calculator once more. We have 5.60 times 12 divided by 4, and also divided by our value for R, which is 0.0821. In this case, we wind up with a temperature that is equal to 205 Kelvin. I'll just bring that back up on the calculator so you can see how we rounded it. Now, as you work through these problems, some of the problems may ask you to do another step. I'll post the answer key in case you have forgotten how to convert to either grams, molecules, or atoms, as some of the problems require. Please let me know if you have any questions, and have a great week.